more times, I really very off to diagnose it's true that 주제에 스포를 쓰는 우리가 외치는 것이니까 일반 지수만 있는 점은 시스템 시스템 그것을 제가 그냥 마인드에 맞추는
Hello everyone, I will be presenting this paper today, Efficient Distributed Training with Full Communication and Computation Overlap. This is the paper CO2 and these are the authors of the paper. It is published in ISLR in 2024. So the introduction or motivation of this paper is basically they works on the problem that training large language models, they requires the massive clusters. So that massive GPU clusters, the high cost barrier, the high speed interconnects such as INFINET, InfiniBand. So they are very expensive, and the traditional training, it suffers from the communication bottleneck when we use the other limited bandwidth networks. So the goal of this paper is to democratize the large scale training and achieve the high scalability on even on the limited bandwidth clusters, just like the 80 GPs TCP. So the solution they provide is the CO2. It basically fully hides the communication behind the computation. Basically, it overlap it entirely in the next round of computation. The core methodology of the CO2 is that they basically based on the two main pillars of the the one is the local updating, and the second one is the asynchronous communication. So as you see in the figure, this is the visualization of the normal standard SGD and their CO2. Uh, in normal, first there is a forward pass and backward pass, and then gradient all reduce operation is applied to synchronize all the gradients, and then this global gradient is updated locally by every GPU, and then the next step, forward pass and the backward pass is happen. But here in CO2, they remove this, not completely remove, but delayed this gradient all reduce or synchronization process by local updating. So after forward and backward pass, every GPU, instead of synchronization globally, they update locally, and then again the next iteration starts, and this they skip this communication step, which used to happen in between the GPUs after every step. So later, after some steps, some predefined steps, they started the asynchronous communication parallelly. So because eventually the results have to synchronize to do the correct training. So in local updating, instead of communicating to the other GPUs, after every single step, each GPU works independently for specific tau steps, and this reduction of frequency of communication. And while GPUs are doing the next steps instead of local updates, next steps of local updates, and the gradients from the previous sets are being sent asynchronously. And here comes the asynchronous part. This asynchronous communication in DDP, in standard DDP, the GPU stops and wait for all reduce function. This all reduce in standard DDP training to synchronize, to perform the synchronization. But in CO2, the sync happens asynchronously in parallel The GPU starts the next computation immediately using its local weights, while the network handles the weight exchange in parallel. So after this, due to their delayed synchronization behavior, they got some problems of the convergence problem in the training. So they also introduced the solution of this convergence problem based on two solutions. First is Stainer's gap penalty and the outer momentum clipping. So uh, this stainless is basically using all weights to calculate the new gradient. So it affects the convergence of the training. So they introduce the stainless gap penalty. It adds the mathematical penalty to the loss if the local weights are very far apart from the global average weight. So this forces the model to stay correct even in the sinking, even when the sinking is delayed or slow. Other solution is the outer momentum clipping. And this is a technique to smooth out the updates, and it prevents the model from making higher jumps in the weight spaces caused by the delayed synchronization. And they achieve the very improved performance based on their proposed solution. This is the result of the throughput based on uh, different internode network configurations such as TCP and RDMA. RDMA is high speed interconnect, and TCP is limited bandwidth interconnect. So this is the standard ADAM with high speed interconnect. It achieves the higher linear scalability, but CO2 with even with the TCP at number of steps 48, they achieve the equal almost 100% scalability, equivalent to this the standard ADAM optimizer. And the second results shows that they use the GPT-2 small model, and they evaluate the training speed and the validation perplexity. So they achieve the higher training speed when they increase the number of toss steps. But due to the less frequent communication, the model achieves the worst generalization effect. So the perplexity of the model goes increase when we increase the toss steps. And also they studied their uh, solution on without their two proposed problem solutions. They also apply the CO2 without penalty and without clipping, which shows the increase in the perplexity as compared to applying these two solutions to the problems. So these two solutions achieve the better performance. So the effect of toss steps in the synchronization, which is the how many steps synchronization should delay. So by increasing the toss steps, as you see it in the perplexity graph, so by increasing this, it improves the communication efficiency, but it reduced the performance of the model. It increased the perplexity also. So they select the optimal tower steps, which is 12 steps, 12 local updates. So they choose this as optimal steps, which effectively overlap computation and communication, and also improve the training efficiency, and also it slightly better regularization effect as compared to the other tau steps. So the conclusion of this paper is they propose the CO2 for efficient large-scale distributed training for limited bandwidth clusters, and it enables the scalability through local updates and asynchronous communication, and they achieve the 100% scalability with the limited bandwidth communication, and they also improve the training scalability using the stainless gap penalty, outer momental clipping, and they provide also theoretical convergence guarantees, and also they extend their work on the they also propose that their work is also implementable on the zero optimizer for memory efficiency. So that is it. If you have any questions and more, I'm explaining this, that why I choose this paper, because in my new research method, I will try to apply this, implement this idea taking from this paper. So that's why this will be considered as a baseline for my research. So if you have any more questions, then you can ask.
I have a couple of questions.
Yes.
Can you go to the previous? Yeah.
Mm.
The word perplexity you keep mentioned. So I want to know the definition of the perplexity in this topic. And the second one is, of course, uh the cus- the this topic is important to improve the speed of the learning or any other ones, but I'm wondering that the performance of the model, this paper displayed just GPT-2, and uh, uh just simply, I want to know whether this method just keep the performance of the model or just to reduce the performance.
Okay, your first question is that why the perplexity used here in this, in which context,
Yeah.
right? So this is the same perplexity which used in the training performance. So they actually mentioned this perplexity to simply tell that by handling this communication and delayed this synchronization, we do not like only do we do on we didn't only do this communication, but also they also tell that how are this handling of communication affect the convergence of the model. So this is the same perplexity which is used in the model training. And also your next question is, sorry, again.
This method just to delay the synchronization process. Am I right?
Yes, yes.
So it means the delayed synchronization means each GPU has different weight of the model.
Mm-hmm.
So my question was, uh, by using this, it reduces the performance of the model or not?
Yes, so in this graph you can see they use the validation perplexity of the model. So they mentioned that when, because they delay synchronization based on this tau steps. So as they increase the number of these tau steps, it means they increase the delay, then the generalization of the model is worsened. The perplexity is higher. So this affects the model performance, but they handle this effect of model performance through the momentum clipping and the stainless gap penalty. So they propose these two solutions to slightly overcome this convergence problem. Any other question?
Okay.
Okay. Thank you for listening.
Yeah.